Welcome to Advanced Spotter Training. In this video, we will delve into the world of radar meteorology. Now this will be a fairly general overview, but there are a lot of excellent resources online should you choose to go beyond this training. So how does radar work? Well, this will be a very simple example, but it will certainly suffice for now. The radar located on the left side of the screen sends out a signal or a pulse. The signal then propagates through the air until it encounters something called a scatterer. Now scatterers can be any number of things, from smoke particles from nearby wildfires, to birds or bugs, to the standard rain and hail. In this case we're looking at a thunderstorm, so the radar beam is encountering raindrops and or hail within this thunderstorm. Once the signal hits these particles, a portion of the emitted signal is sent back to the radar. The radar then retrieves this portion of the reflected signal and uses it to piece together a radar image. The stronger the return signal, the heavier the precipitation. This example shows a single radar elevation at a specific time, but radars are constantly scanning and retrieving over 360 degrees. Once the radar makes a full revolution, it will increase the angle at which it is scanning, giving a more three-dimensional radar depiction. Once the radar has made several revolutions at several angles, something called a radar volume is complete. This will be important in the next slide, so remember it, radar volume. We begin with reflectivity. This is the radar parameter that you're probably most familiar with. Reflectivity, as stated before, is a depiction of precipitation. Colors range from light blue or green to a dark red or purple. Of course, this can vary depending on which source the data is coming from, as color tables can be easily changed. There are also two basic types of reflectivity, base and composite. Radar works by sending out signals at varying elevations. Assuming there's something out there to reflect that signal, a portion of the original signal will be sent back to the radar, as we saw in the illustration before. Larger and or more closely spaced precipitation particles will reflect more of that energy back to the radar, giving them a higher reflectivity. Base reflectivity, as seen on the left side of the screen, is taken at a single elevation. Composite reflectivity, on the other hand, is a conglomerate of all radar elevations. Remember, we call this a radar volume, or a volume scan, in which the greatest reflectivity for a specific location, or radar bin, is displayed. The two images here show how base and composite reflectivity vary, as both images are from the same radar at the same time. You may notice base reflectivity provides greater detail and is higher in spatial resolution. Composite reflectivity tends to be a bit more blocky and may hide important low-level features, though both can be beneficial. This image, which comes from the Oklahoma Climate Survey, shows a zoomed view of one of the storms on the last slide. This is the historic Moore, Oklahoma supercell of May 3, 1999. Note the base reflectivity image and how it compares to the composite image. The base image from Tilt 1 shows a much higher resolution depiction of the supercell with a very clear hook echo. The composite image does not show this, but it does indicate the presence of an intense hail core and the likely presence of severe hail. When looking at low-level features iconic to supercells, composite reflectivity is almost worthless, but it does provide some idea of storm severity. We now move on to the second important radar attribute, velocity. Reflectivity gives us an idea of where storms are located and whether they contain light, moderate, or heavy rain and or hail. But reflectivity does not tell us anything about damaging wind potential or whether the storm is rotating. For this, we must use velocity. Velocity is determined by the movement of precipitation particles within thunderstorms. Two primary colors are used to depict velocity, green and red. Green indicates that precipitation particles are moving toward the radar, or that winds are blowing toward the radar. Conversely, red indicates winds moving away from the radar. This gets a bit tricky because the radar is a point, and the way that the radar beam sweeps out in a circle can make certain velocity signatures difficult to discern based on where the storm is located with respect to the radar. Just like reflectivity, there are two main types of velocity, base velocity and storm relative velocity. Base velocity is simply the wind speed and direction with respect to the ground. Storm relative, as you may have already guessed, is wind speed and direction taking into account the movement of the thunderstorm. In the two images above, we are looking at a radar couplet, which indicates rotation. The base velocity shows some weak low-level rotation, indicative of a mesocyclone, but perhaps not a tornado. However, if we take the storm's forward motion into account, the velocity couplet becomes much more impressive, and a tornado vortex signature becomes obvious. We're throwing around a lot of complicated terms here, but you will become more familiar with them as we move through the presentation. Just remember that base velocity is ground relative, and storm relative motion, or SRM, is storm relative. Here we see an image showing the difference in base and storm relative velocities for the same storm. The image in the upper left portion of the screen is base velocity, and shows what appears to be a very weak circulation. We see two shades of red with the radar located southwest of the storm. It's important to know where the radar is located to get an accurate idea of what's happening within the storm. Reds indicate winds moving away from the radar, which would be to the northeast. The brighter the red shading, the stronger those winds are. So we see strong outbound velocities adjacent to weaker outbound velocities. It may take some imagining here, but that means there is some sort of circulation within the storm. In this case, it's a cyclonic or counterclockwise circulation. But because we are looking at ground relative winds as this storm appears to be moving quite fast, the circulation is somewhat masked. Now, compare this image to the storm relative velocity image in the upper right corner of the image. Here we see a large area of outbound velocities adjacent to inbound velocities. Note the red and green colors adjacent to each other. This is a much clearer depiction of the mesocyclone and gives some idea of how strong the circulation is. On big, severe weather days when tornadoes are possible, we use storm relative velocity much more frequently than standard velocity, though base velocity can be very useful on days when damaging winds are more likely. Alright, now that we've covered our bases on radar reflectivity and velocity, we can delve into what some of this data looks like under varying conditions. Here we see the three main storm types as depicted in radar reflectivity. The most basic type of thunderstorm is called the pulse storm. The reason it's described this way is because these storms tend to develop and collapse quickly, pulsing up and down. The second type of storm, which requires more organization than pulse storms, are multicell storms. These are not individual storms, but rather storm systems made up of multiple smaller storms. Squall lines and mesoscale convective systems would fit into this category of thunderstorm type. The final and most severe storm type is the supercell. This will be the main focus of this training, though we will touch briefly on the other storm types before moving on to supercells. You can quickly see differences between these storm types, and there are really only a handful of environmental factors that affect what kinds of storms will develop on a given day. Wind shear and instability are the big ones. We will discuss this more toward the end of this lesson. As we mentioned before, pulse storms collapse almost as quickly as they go up. These storms form when there is little to no environmental wind shear, but adequate instability and moisture. Notice the reflectivity image on left shows some fairly high radar returns with the orange and red colors. Some pulse storms may contain hail, but there is rarely ever rotation with these storms. In fact, the greatest threat from pulse storms is damaging wind gusts. The image at right shows two divergent velocity signatures, areas where inbound velocities in green are closer to the radar than outbound velocities in red. We call this a downburst or microburst signature. These signatures don't always indicate severe winds, but given the right conditions, as pulse storms collapse, they may produce damaging winds. Pulse storms are common in Oklahoma and Texas, especially during the mid to late summer months. And it's not uncommon for the worst pulse storms to create 70 to 80 mile per hour wind gusts as they collapse. Contrary to pulse storms, multicell storms or storm complexes require at least some wind shear to develop. As individual storms collapse, they produce what's called outflow. With successive thunderstorm development and collapse, thunderstorm outflows merge, creating what's called a cold pool. The outflow acts as a front, creating additional storms, and as these storms collapse, the cold pool and outflow are strengthened. Multicell storms often produce sporadic severe weather, including wind damage and large hail. On the extreme end of the multicell spectrum are derechos. Derechos are essentially squall lines that produce widespread, significant wind damage. These systems often contain bow echoes or areas of enhanced severe winds within the greater complex. The diagrams here show the evolution of a multi-scale convective system, or MCS. The complex begins as a single cell or cluster of closely spaced cells. As outflows from these storms merge, new storms develop, and a cold pool develops. Storm complexes often take on a comma shape over time, as illustrated here. Sometimes individual storms within multicell storm complexes can produce tornadoes. However, they are normally brief and fairly weak. In this slide, we see two examples of mesoscale convective systems as they would appear on radar. The animation at left is a reflectivity loop, which shows a comma-shaped area of storms extending from Broken Bow to Mullen, Nebraska. On the backside of this line of storms is an area known as the stratiform precipitation region. This area is actually where something called a rear inflow jet develops. The rear inflow jet is what ultimately keeps the storm system going and also produces severe winds at the storm's leading edge. Now, we won't go into this feature in too much detail, but it is worth looking up if you find some extra time. The image on the right shows both reflectivity and velocity for a fairly compact severe storm complex. This could be referred to as a bow echo, though many bow echoes are smaller than this one. Reflectivity shows an arc of heavy precipitation and hail oriented southwest to northeast. At the same time, the velocity image shows an area of inbound winds along the leading edge of the heaviest storms. These winds are in the 60 to 70 mile per hour range, so some wind damage is likely with this storm cluster. Note that we are referring to base velocity, not storm relative velocity, because we're more concerned with damaging straight line winds than tornadoes. The final storm type, and the one that we will devote most of our time to in this training, is the supercell. We start here with an overhead schematic of a supercell, and we can easily match this diagram to an actual radar image from a supercell in central Oklahoma. Now, we've already used this image in previous trainings as well as in this one, so it should look familiar by now. This is an ideal example of what a supercell looks like in reflectivity. Many are not this well defined, and that's why it pays to have a basic understanding of radar reflectivity and velocity signatures, because it's not always going to look this clear-cut. There are many clear differences between this reflectivity presentation and the ones we've recently seen with pulse storms and multicell storms. For one, we see a clearly defined hook echo on the south and west parts of the storm. We'll discuss a bit more on how these develop in just a few minutes. We also notice a large rain-free area arcing into this hook echo. This is called the inflow notch, or inflow region of the storm. There's very little precip in this area because it's where the strongest updraft is located, so all of the precipitation particles, including large hail, are being lofted upward and suspended above the radar beam. Moving on to the most prominent feature, the precipitation area, we note that most of the precip is located to the north and east of the main updraft. This is very typical of classic tornadic supercells. Environmental wind shear acts to loft precip particles down shear, which in this case is to the north and east. This ensures that precipitation and associated rain-cooled air do not fall into the thunderstorm updraft. If this were to happen, the storm would lose its source of inflow and would be cut off, causing it to weaken and ultimately die. Because the heaviest precipitation is located away from the updraft region, the supercell is able to last for hours and hours and travel many miles without weakening. Finally, in extreme cases such as this one, a reflectivity ball or debris ball may be noted at the end of the hook echo. In this image, the ball of high reflectivity was associated with tornado debris being lofted far into the sky. The radar detects the debris just as it would any other precip particles, and because tornado debris is often much larger and more closely spaced than rain or hail, it generates a higher reflectivity. Now, these will not always be apparent, even in tornado-producing supercells. Related to the thunderstorm updraft is an area known as the weak echo region, or WER. This area is coincident with the inflow notch and the area of most intense thunderstorm updraft. Because vertical winds are so strong here, precipitation particles are lofted far into the atmosphere, resulting in an area of little to no reflectivity adjacent to the hook echo. This is seen in the lower elevation scans of the radar. As we ascend in elevation, more of these precipitation particles become apparent, and in the most intense supercells, a bounded weak echo region, or BWER, may be present. The BWER is an area of weak or no reflectivity surrounded by high reflectivity as seen in the image at right. It resembles a donut. If observing a storm with a BWER, be very careful that you stay well away from the precipitation core. BWERs indicate extreme vertical motions, enough to suspend very large hail particles such as baseballs and softballs. BWERs also indicate a greater likelihood of tornado development. Here we see a vertical cross-section through a BWER. Note that this supercell does not have the same classic hook look as the initial example we saw. A small but noticeable weak echo region is present on the southwest side of the storm, and as we look in the vertical, we see high reflectivity suspended above the area of weak reflectivity. This indicates a very strong updraft, and large hail is likely with this storm. Now we will discuss hook echoes more in depth. Here we have two examples of well-defined hook echoes. The image at left is from the standard radar the Weather Service offices around the country use during severe weather. The image at right is a high-resolution image from a Doppler on wheels mobile radar. Hook echoes are sickle-shaped protrusions of precipitation that form due to the low-level rotation pattern within the supercell. Rear flank downdrafts are instrumental in forcing precipitation around the mesocyclone in a counterclockwise fashion. This is what creates the appendage that juts out into the inflow region. On right-moving supercells, hook echoes are normally located on the southwest side of the storm, while left-moving supercells display hook echoes on the northwest side. We will go into more detail on right and left-moving storms in a few moments. Notice the high-resolution image contains a small donut hole within the hook itself. This is actually a tornadic signature. The high reflectivity surrounding the tornado is likely a mixture of precipitation and small debris particles. Notice that the tornado is located on the north side of the hook echo, as this is where the low-level rotation is maximized. Just because there's a hook does not mean there's a tornado. There are many supercells that produce substantial hooks that never produce tornadoes, though damaging winds and large hail are almost a certainty within the RFD. So now that you have a better understanding of hook echoes and reflectivity, let's look at an example using velocity. The radar images above are from the May 24, 2011 Central Oklahoma tornado outbreak. The two hook echoes circled were indeed associated with tornadoes. Note the balls of heavy reflectivity. These are actually debris balls associated with two violent tornadoes that occurred near Chickasha and Goldsby. Analyzing the velocity image at left, notice the location of the radar to the northeast of the storms. This means that inbound winds will be from the southwest and outbound winds will be from the northeast. And what type of velocity are we assessing here? You guessed it, storm relative velocity, because we're interested in low-level circulations and tornado potential. In each of these hook echoes, we have extremely strong inbounds adjacent to moderate outbounds. These are not only low-level mesocyclone signatures, but are what is termed a tornado vortex signature, or TVS. More on those later. Being able to quickly look at a radar image such as this and point out the most important features is critical in storm spotting. It will not only make you a better spotter, but also a safer one. We've already touched on this briefly, but a mesocyclone is essentially a rotating thunderstorm updraft. To detect mesocyclones, we refer to velocity data, typically storm relative, though mesocyclones can be detected through standard base velocity as well, just not as clearly. Here we see two examples of mesocyclones. The example at right would be classified a relatively weak mesocyclone. Note the inbound and outbound velocities aren't all that strong. This storm is definitely severe, but tornado potential is assumed to be relatively low unless visible confirmation is obtained. The example at left, however, depicts an intense mesocyclone and tornado vortex signature, though we haven't gotten to that just yet. Not only is it likely that a tornado is ongoing with this signature, but the tornado is probably strong to violent based on the extreme velocities we're observing here. Within the spectrum of mesocyclone size, strength, and longevity lie the mesovortices. These are very small-scale, transient circulations that are normally associated with squall lines or thunderstorm clusters. While these can occasionally produce very brief tornadoes, substantial swaths of significant wind damage are much more common. Alright, so let's look at a real-world example. This radar image should look pretty familiar to you. It's the velocity image we saw about 2 slides back on mesocyclone strength. When velocities are this strong, we actually have a new classification known as the tornado vortex signature, which I've already mentioned a couple of times. In order for this signature to be present, the velocity difference across two adjacent velocity pixels, or radar bins as we call them, must be at least 90 knots or around 103 miles per hour. In this example, we have inbound velocities of 80 knots adjacent to outbound velocities of roughly the same speed. This means our velocity difference, or gate-to-gate shear, in this small area is approximately 150 to 160 knots, or 170 to 185 miles per hour. For context, we have a photo of the tornado that occurred with this signature. You may recall the Greensburg, Kansas tornado of May 4, 2007, which wiped out about 90 to 95% of Greensburg, Kansas, and was rated an EF5 on the enhanced Fujita scale. Outside of mesocyclones and supercell structures, there are other velocity signatures worth noting. These two are convergent and divergent signatures. Convergence is simply winds coming together, often indicating locations of fronts or boundaries, or strengthening thunderstorms. Divergence is just the opposite and sometimes indicates a collapsing storm and potential for wind damage. Sometimes these signatures are mistaken for mesocyclones, and that's why it's very important to know exactly where the radar is located with respect to the area of interest, as this can result in misidentification. We're now going to move on to more dynamic processes with supercells rather than just simple radar signatures. However, understanding these dynamics is important in deciphering radar trends in supercell evolution, especially if you're out there spotting. The images above show a hypothetical three-dimensional rendering of a supercell thunderstorm. On the left side of both images, a representation of wind with respect to the storm is displayed. Note how winds increase with height, indicating what we call wind shear. This shear creates a horizontally rotating tube of air, sometimes called a vortex tube. As the storm develops, its updraft tilts the tube in the vertical. This forms a vortex pair, one rotating clockwise and one rotating counterclockwise. Assuming wind direction does not change that much with height, both of these circulations will intensify. A downdraft will then develop between the two, leading to a separation of thunderstorm updrafts. We call these splitting supercells. In the northern hemisphere, severe weather conditions normally favor the counterclockwise circulation, which is referred to as the right-moving storm. The clockwise rotating supercell is termed the left-moving storm. We'll see why here in the next few slides. We plot the wind changes with height on something called a hodograph. While the formation of the hodograph really isn't all that important for spotting purposes, it is important to know the three main types of hodographs that favor supercells and what you can expect to happen when storms begin to develop. When wind speed increases with height but there's little change in wind direction, we call this a straight line hodograph. This type of pattern favors mirror image splitting supercells. One glance at the time series above shows how one cell splits into two through time. One cell moves to the north, the left split, and the other moves to the south or east, a right split. The right moving storm, however, persists and often lasts many hours. When winds both increase and veer, or shift from south or southeast to west or southwest with height, we call this hodograph clockwise-curved. You can see by the clockwise-shaped arc in the hodograph in the upper left part of the image. This type of wind pattern favors the right-moving supercell. This kind of wind shear is what we normally see on the big severe weather and tornado outbreak days. Notice that left splits tend to weaken rapidly once they move away from the dominant southern storm. Finally, we come to the very rare, especially in the northern hemisphere, counter-clockwise-curved hodograph. In this case, we would have north or northwest winds at the surface and west winds in the mid and upper atmosphere. As you can see in the image, this type of wind pattern favors the left splitting storm, and the right split rapidly dies as the storm moves east. This is much more common in the southern hemisphere with large tornado outbreaks there. Here we see a real-world example of splitting supercells. We have the dominant right-moving supercell in the center of the screen. Note the large, heavy reflectivity core and the broad hook echo with this storm. However, to the north of this storm is a smaller supercell that split off the dominant storm to the south. The arrows indicate the storm motion. So clearly, based on the intensity of the main storm, we can expect some rather large hail with this storm. And we can see from the pictures that there was indeed some very large hail with the right-moving storm. So exactly what kind of hazards present themselves with these splitting storms? Well, the right-moving supercell is normally the one that's going to produce more significant severe weather, including tornadoes. The left split may on rare occasion produce tornadoes, but it's normally known more for very large to extreme hail. Splitting storms and storm mergers are a real challenge for storm spotters and safe positioning. The white arrows indicate storm direction. Note the cell in the lower left portion of the image. This storm will likely merge with the storm in the center of the image at a later point in time. The X's on the screen represent varying storm spotter positions. If you're positioned at the pink X, the left split is headed your way and you can bet on some very large hail. At the white X, you may be on a more interesting storm, but because you're looking into the precipitation core, you're not going to be able to see the interest area of the storm. The red X marks the best location to observe the most intense area of the dominant supercell. But caution should be stressed here, because these storms often take hard right turns and may move toward this location, especially as low-level rotation is increasing prior to tornado formation. Another consideration is that the storm at the bottom left of the screen may merge with the storm in the center of the screen, so it may close on your position if you're at the red X. So just to recap, remaining well to the south and east of the hook echo and inflow area is the best place to observe supercells for rotation and tornado formation. Make sure you're paying attention to other storms around you, as there is rarely only one significant storm to worry about. With spotter positioning in mind, it's important to discuss outflow boundaries and their role in enhancing tornado potential. Outflow boundaries act as a source of low-level spin for supercells, and if these storms interact with the boundary in just the right way, they can become tornadic in a hurry. The image above illustrates how this process works. Initially, the boundary is removed from the thunderstorm. As the storm approaches the boundary, or the boundary drifts toward the storm, horizontal vorticity is lifted along and behind the boundary. This is then drawn into the storm, increasing its rotation. At the same time, cloud base is lower because air along and just behind the boundary is normally cooler than the air ahead of it. This causes clouds to form at a lower elevation, ultimately lowering the cloud base. With lower cloud bases and stronger storm rotation, tornado potential increases. Storms can become tornadic in a hurry along boundaries, and it's critical to pay attention to them if you're out spotting. In this real-world example, a storm intersects with an outflow boundary in the upper left portion of the top image. We see a well-defined hook echo in reflectivity and a strong velocity couplet in the bottom image, indicating the presence of a tornado. Note the area of convergence along the boundary indicated by the long stretch of inbound and outbound velocities coming together. The last thing we will discuss as far as thunderstorm types are concerned are elevated thunderstorms. We actually just saw an example of these kinds of storms on the last slide. Elevated thunderstorms form above a layer of stable air where atmospheric instability resides. On the last slide, the area behind the outflow boundary was stable at the surface, but because there is still instability above the stable layer, the storms continue. These are called elevated storms because they do not draw their energy from the surface air mass. The image above shows an atmospheric sounding. The green line denotes atmospheric moisture, while the red line depicts the temperature. Now don't get too caught up on the details of the plot. It's very confusing. Just understand that the area below the steep temperature increase, called an inversion, is where the stable air mass is located. The air above this, however, is still unstable. Depending on the amount of instability, elevated thunderstorms can produce large hail. But storm rotation is not able to penetrate this stable layer near the ground, so they never produce tornadoes. We will finish up this lesson by discussing a relatively new radar technology known as Dual-Pol radar. Standard Doppler radar only scans in the horizontal. This is fine for most radar interpretation activities, but it only provides a two-dimensional aspect on precipitation. In order to obtain additional information, the radar must send out both horizontal and vertical pulses. This is known as dual polarization, or simply dual-pol radar. Because we are scanning in two directions, we can now discern three-dimensional properties of precipitation particles. Since this is still somewhat new, we're still looking at ways to incorporate this data into our radar interpretation skills, but we figured we'd at least give you a taste. For now, we'll just focus on one simple example of what dual polarization data look like. Here we have a 4-panel layout for a tornado-producing supercell. We're going to focus in on something called the tornado debris signature. The idea of the TDS is simple. The radar detects tornado debris as it's being lofted inside the tornado through a parameter called correlation coefficient, or CC. CC is a way of measuring the similarity of precipitation particles within a storm. If the CC value is close to 1, the particles are very similar in size and shape. But when CC values fall below 0.7, the particles are very dissimilar. Rain and snow will have high CC values because they're usually very similar in size and shape. But tornado debris can vary wildly in shape and size. The example above shows both reflectivity and velocity in the upper two panels. Reflectivity contains a large hook echo, and velocity indicates a strong rotation signature co-located with this feature. Don't worry about ZDR in the lower left, but do pay attention to the circle-shaped area of very low correlation coefficient in the bottom right portion of the image. This is the radar sensing debris within the tornado itself and indicates that the tornado is ongoing and has caused some kind of damage as debris is present. Take note. Debris signatures that last for a long time likely indicate the presence of a strong or violent tornado. Storms with a persistent TDS or several TDSs should be given extra room to breathe, as erratic storm movements may quickly put you in a dangerous position. Here's another example from the tornado that struck Moore, Oklahoma on May 20th, 2013. Note the high reflectivity in the upper left and very strong couplet in the upper right portion of the image. In the bottom left panel, correlation coefficient shows a circular area of very low values associated with debris being lofted by the tornado as it moves east of Newcastle. After looking at several radar scans in the vertical, it was noted that this tornado lofted debris up to around 4 miles above the ground. The bottom right panel shows the final tornado path from the ground survey, which confirmed the tornado was among the strongest on the enhanced Fujita scale, an EF5. Alright, now that we've trudged through all of the technical stuff and all of the different radar parameters, we're going to go through a quick radar simulation to sum everything up. This will touch on pretty much everything we've learned in this module. Many of you may recall the incredibly wide tornado that struck rural areas between El Reno and Union City, Oklahoma on May 31, 2013. In this series of images, we will only look at the half-degree reflectivity and storm relative velocity images from around 6 p.m. to 6:45 p.m. Central Daylight Time. We turn first to the reflectivity image on the right. Note the area of very high reflectivity north of I-40 and west of El Reno. This likely indicates an area of hail. And we also see this drops off dramatically to the south in an arc-shaped fashion. If we were to observe reflectivity at higher elevation scans, we would see a clear weak echo region and bounded weak echo region in this area, consistent with supercell structure. We would expect very strong inflow in this area, and turning to velocity at left, we see this is indeed the case. In fact, the inflow at this level is so strong, the radar has interpreted it to be an inbound signal, moving out of the storm, and we know this is not logical. This is a velocity artifact that sometimes occurs with obscenely strong velocities. Looking more closely at the velocity image, we do see a somewhat weak but tight circulation developing. A brief tornado had been reported just a few minutes prior to this scan, and if a tornado had still been ongoing, this is exactly where it would have been. 5 minutes later, we have a much more impressive signature, both in reflectivity and velocity. Notice the hook echo forming on the southwest side of the storm, just to the south of that reflectivity gradient we spoke of earlier. This indicates a rapid organization of the storm. Now turning to velocity, we have a clear TVS with impressive inbounds and outbounds right next to each other. We also see the persistent area of inflow to the east of the tornado. This should tell us that this supercell has a strong source of fuel and energy and is not likely to weaken anytime soon. And given the moist, unstable air moving into the storm, it may produce more than just this one tornado. And as if you hadn't already guessed, this is where the tornado would have been located. As we move through time, we continue to see this very impressive reflectivity and velocity structure. The velocities actually become quite complex at times because this tornado is so large and contains multiple smaller circulations within the parent tornado, a multiple vortex tornado, or multivortex. Finally, the tornado reaches I-40 and becomes nearly stationary. Note the TVS sitting right on the interstate between El Reno and Yukon. Turning to reflectivity, it is apparent that the tornado is completely rain-wrapped. Nothing in the reflectivity image alone would tell you a tornado is present. This is why velocity is so critical in the warning process and in safe storm spotting. This is a classic example of a storm that should prompt you to keep your distance. Erratic changes in speed and direction of the tornado resulted in several fatalities as people were struck by the tornado in their vehicles on the rural roads south of El Reno. The velocity couplet finally weakens at around 6:42 p.m. Central Daylight Time, though other weak circulations persist well into the evening. We also see several other storms developing back to the west, and these storms continued into the overnight hours, producing flash flooding in many locations. We'll finish with an animation from the historic May 20th, 2013 tornado that struck Moore, Oklahoma. In this animation, we'll only look at reflectivity, but rest assured the velocities were just as impressive. Notice the long arcing hook that wraps into the high reflectivity ball just southwest of Moore. These high reflectivities are due to a very high concentration of tornado debris being sensed by the radar. Often these are referred to as debris balls, and we've seen a couple examples of these in earlier slides. As the animation plays, one can see the individual reflectivity elements spiraling into this area where the tornado resides. The tornado dissipates to the northeast of Moore, but as debris continues to fall from the sky, we see an area of high reflectivity where the tornado has lifted. Well, that brings us to the end of our presentation on radar interpretation. Thanks for your attention. Hopefully you're more equipped to understand what you see on radar, ultimately keeping you and others around you safer while storm spotting. The next section of the Advanced Spotter training will focus on where to find information for basic severe weather forecasting.